Hi my dear students, today we are going to discuss very important organic chemistry, general organic chemistry and hydrocarbons and first year chapters. So very easy to gain the marks from organic chemistry if you know the logics. So first question, see the first question. In which of the following hyperconjugation is not possible? So first hyperconjugation. First which contains alpha hydrogens that means alpha hydrogens means which contains alpha carbon which is attached to sp2 carbon. So the hydrogens, alpha hydrogens which is attached to the alpha carbon atom, alpha carbon which is attached to the sp2 carbon, those molecules only exhibits hyperconjugation. For example CH3 CH double bond CH2. So it is sp carbon, sp2 carbon, it is sp2 carbon, it is sp3 carbon. It is functional group. CH double bond CH2 is functional group which has CH3, it is alpha carbon. This alpha carbon has hydrogens. That hydrogens only delocalization through double bond. They are involved in delocalization of sigma electrons with adjacent double bond is called hyperconjugation. So here how many hyperconjugative structures are possible means 3 hyperconjugative structures are possible. So like that CH3 CH2 plus, it is also sp2 carbon atom. CH3 CH2 plus, it is also sp2 carbon atom. It is sp3 carbon. How many hydrogens are there? Alpha hydrogens. So 2 hydrogens. So 2 hyperconjugative structures are possible. How many alpha hydrogens are there? That number of hyperconjugative structures are possible. Hyperconjugation is also called as no bond resonance. So no need to learn this type of matter. So how to identify which gives hyperconjugative structures means in these 4 which does not have alpha hydrogens. So if you observe first option, C, it contains 3 CH3 groups. It is sp2 carbon. Double bond carbons are sp2 carbons. It is sp3 carbon which is attached to directly sp2 carbon, which does not have hydrogens, which directly linked with carbon atoms, does not have any hydrogens. That means no alpha hydrogens. If there is no alpha hydrogens, does not show hyperconjugation. So does not show hyperconjugation. So very easy. Remaining all you observe, it is, if you observe remaining all, it is sp2 carbon which is attached to the sp3 carbon. sp3 carbon having 1 hydrogen. So that means alpha carbon, 1 alpha hydrogen is present. It gives 1 hyperconjugative structure. It is alpha carbon, it has 2 hydrogens are present. So 2 hyperconjugative structures are possible. It is sp2 carbon, this sp2 carbon have sp3 carbon, that means alpha carbon. It have 2 hydrogens, 2 alpha hydrogens, 2 hyperconjugative structures are possible. So which does not gives hyperconjugation means which does not have alpha hydrogens. They does not show hyperconjugation. So answer is A. So answer A. Okay. Next one. The correct order of the stability of the following based on hyperconjugation. Again hyperconjugation. Same model question. If you observe first one, cyclohexane which contains CH double bond CH2. So here CH2 double bond CH2 sp2 carbon, it is also sp2 carbon. The sp3 carbon which is attached to sp2 carbon. So it is sp3 carbon which is attached to sp2 carbon. So how many hydrogens are present this carbon atom, sp3 carbon atom? Here only one hydrogen, because 1 2 3 already 3 bonds are there, fourth bond is hydrogen, so it gives one hyperconjugative structure. Second one, it is sp2 carbon, it is also sp2 carbon. sp3 carbon which is attached to sp2, sp3 carbon which is attached to sp2 carbon atom, that means alpha carbon. This carbon has already 2 bonds, remaining 2 hydrogens. So this carbon has 2 bonds, remaining 2 hydrogens. So total how many hyperconjugative structures? 1 2 3 4. 4 hyperconjugative structures are given. Remaining these carbons are not given by hyperconjugation structures. Why? The sp3 carbons which are directly attached to sp2 carbon only gives hyperconjugative structures. So next, third one, double bond CH3. It is sp2 carbon, it is sp2. sp3 which is attached to sp2, sp3 which is attached to sp2. It is also sp3 which is attached to sp2. So how many carbons are there? 3 carbons. Next, hyperconjugative structures gives hydrogens. Here 1, here 1. 2 hydrogens. Here 1, here 1. 3, 4 hydrogens. Here 3 hydrogens. Total 3 plus 4, 5, 6, 7. 7 hyperconjugative structures. Hyperconjugative structures. Last one, double bond CH3, CH3. So same, sp2 carbon, sp2 carbon. sp3 carbon which is attached to sp2. So it is sp3. So it is sp3. So here 2 hydrogens, 2 hydrogens. Here also 2 hydrogens. Here 3 hydrogens, here 3 hydrogens, because it is sp3 which is attached to sp2. It is sp3 which is attached to sp2. 3, 3, 6, 7, 8, 9, 10. So 10 hyperconjugative structures are possible. So according to the hyperconjugative structures, how many hyperconjugative structures are there? That more stable, that most stable. So number of hyperconjugative structures are more stable, most stable. So 10 hyperconjugative structures. So fourth one, high hyperconjugation. So fourth one is greater. So all are 4. Next, after 4, 7 hyperconjugative structures. 3. So 4, 3. Next 2. Finally 1. 4, 3, 2, 1. So answer A. Very easy hyperconjugative stability. Which one is more stable? Means more number of hyperconjugative structures, more stable. More stable. Less number of hyperconjugative structures, less stable. Okay, note this. Say the next question. The stability order of given alkanes is again same, hyperconjugation, based on hyperconjugation. It is sp2 carbon, so it is sp2 carbon, so it is sp3 carbon which is directly attached to sp2 carbon. Here how many hydrogens? 1, 2. Here also 2. So total how many hyperconjugative structures are possible here? 4. Here 4 hyperconjugative structures are possible. Next, here it is sp2, it is also sp2. The sp3 carbon which is directly attached to sp2, so only 1. Here also sp3 carbon which is directly attached to sp2, here also 1. Here how many hydrogens? 1, 2, because already 2 bonds are there. So here 2 hydrogens, here already 3 bonds are there, extra 1 hydrogen. So total 3 hyperconjugative structures. 3 hyperconjugative structures. Here 2, 4 hyperconjugative structures. Here it is sp2, it is sp3, it is sp3, it is sp3 which is attached to sp2 carbon, which is sp3. So here how many hydrogens? 2. Here how many? 2. Here 2. So here also 2. So total how many? 1, 2, 3, 4, 5, 6, 7, 8. Very easy. sp3 carbon which is attached to sp2 carbon, sp3 carbon which is attached to sp2 carbon, like that 4. So each carbon has 2 hydrogens, so total 8 hyperconjugated structures, 8 hyperconjugated structures. So which one is highly stable, which one gives more hyperconjugated structures, that is more stable. So third one is highly stable. So 3 is greater, next one 1, 3 is greater than 1 is greater than 2. So option D, 3 is greater than 1 is greater than 2. Next one, in the conversion of A to B, the electrophile involved is, so first one C2H2, C2H2 means CH triple bond CH, acetylene. When acetylene is passed through red hot iron tube, already you learn the preparation of benzene, red hot iron tube. In the preparation of benzene, when acetylene gas is passed through red hot iron tube, on polymerization of 3 moles of acetylene, it forms benzene. So A is benzene. Benzene again reacts with acyl chloride, CH3COCl, in the presence of AlCl3. It is called Friedel-Crafts acylation. If CH3COCl is there, Friedel-Crafts acylation, in the presence of AlCl3 catalyst, anhydrous AlCl3. If CH3Cl is there, that is Friedel-Crafts alkylation. So here Cl minus CH3C double bond O plus. The electrophile is CH3C double bond O plus. Then it forms COCH3 plus H plus and Cl minus HCl. It is called acyl benzene or acetyl benzene. So here the electrophile is CH3C double bond O plus. Okay, note this. See the next question, very easy, very easy. Arrange the following in the correct order of their acidic strength. Very easy. So how to find acidic strength of different hydrocarbons? Only carbon hydrogen containing compounds are called hydrocarbons. Different hydrocarbons are there. Double bond is present, alkene. Triple bond is present, alkyne. Triple bond, alkyne. Single bond, CC single bond is there, alkane. So acidic strength order is, for alkynes is more, alkynes is greater than alkenes, alkenes acidic strength is greater than alkanes. Alkynes means C triple bond C, C double bond C, C single bond C. How do you find C triple bond C is more acidic strength? Because of percentage of S character. If S character is more, so that it has more acidic strength. If S character is less, that it has less acidic strength. So you know that triple bond has Sp, hybridization Sp, double bond has Sp2, single bond has Sp3. Here percentage of S character is, percentage of S is 50 plus 50. If you add total percentage 100, S is 50, P is 50. So S character 50%. So here total how many orbitals? 2 p orbitals, 1 s orbital, 3 orbitals. Total is 100. 100 by 3. Percentage of S is 100 by 3, 33.33% here. Sp3, how many orbitals? 3 p orbitals, 1 s orbital. Total 4 orbitals. So percentage of S is 100 by 4. 100 by 4 means 25. So which one has high percentage of S character? Percent of S character is directly proportional to acidic strength. So in which one has highest percentage of acidic strength? Triple bond. So in these two, which one has more acidic strength? If the electron donating groups are attached to the alkyl groups are attached to the triple bonded carbon atom, it has a less donate to H plus ions. If electron withdrawing groups are attached to the triple bonded carbon atom, then it strength of donation of H plus ions is more. So CH3 group is electron donating group. That's why when compared to this one, acidic strength is less. So first one 2. So higher acidic strength is 2. So next 3. So next when compared to these two, alkynes has more acidic strength. Finally 4. So answer is 2 is greater than, 3 is greater than, 1 is greater than 4. 2, 3, 1, 4. Okay, if you observe next question, the major products P and Q formed in the following reactions are very easy. It is the benzene properties. Already you learned in first year benzene chemical properties. Benzene reacts with alkyl halide in the presence of catalyst anhydrous ClCl3 forms alkyl benzene. If here CH3 is present, CH3Cl is present, then methyl benzene is formed. If ethyl group C2H5 is present, ethyl benzene is formed. But if it is a propyl group, first it forms CH3, CH2 positive, Cl minus. After that, one hydrogen is rearranged to carbocation. One hydrogen is shifted to carbocation, primary carbocation, and forms CH3, CH positive, CH3. It is secondary carbocation. It is primary carbocation. When compared to primary carbocation, secondary carbocation is more stable. So that's why in first reaction here CH3 is formed. So it is called isopropyl benzene. Isopropyl benzene, another name cumene. So cumene is formed in first reaction. In second reaction, you observe benzene reacts with CH3Cl in the presence of anhydrous ClCl3. So again it is Friedel-Crafts alkylation. So CH3 plus attacks on benzene, it forms methyl benzene. So it reacts with the bromine in the presence of sunlight. In the presence of sunlight means free radical substitution on sp3 carbon atom. It is sp2, double bonds are present, these are all sp2 carbon atoms. It is only sp3 hydrogen is replaced by bromine atom. So then it forms CH2Br, here minus HBr. One hydrogen, one bromine, HBr elimination. So one hydrogen is replaced by bromine atom. It is a benzylic carbon, benzylic hydrogen. So that's why it is called benzylic substitution. So CH2Br is formed. If you add aqueous KOH means Br minus is replaced by OH minus. So then it forms CH2OH. So benzyl alcohol is formed. So final product is B is benzyl alcohol, A is isopropyl benzene, cumene. Okay, not this. Question: the major products P and Q in the following reactions respectively are: alkyne is given, triple bond is present in between C and C, that is alkyne. H2 Lendlar's catalyst, sodium and liquid ammonia. So remember, hydrogenation in the presence of Lendlar catalyst, that means palladium barium sulfate in quinoline. Palladium barium sulfate in quinoline is called Lendlar's catalyst. In the presence of Lendlar catalyst, alkynes are reduced to alkanes. They are cis alkanes. If sodium liquid ammonia is present, trans alkane is formed. So if Lendlar's catalyst is used, cis alkane is the answer. If sodium and liquid ammonia is present, that is trans alkane. So P is cis alkane, Q is trans alkane. So answer is C. Very easy. Next one. The major product formed is, so first one, CHBr, CH2Br. So CHBr. Alcoholic KOH. What is the use of alcoholic KOH? Alcoholic KOH is used to dehydrohalogenation. Dehydrohalogenating agent. That means one hydrogen and one halogen is removed. So one halogen, one hydrogen. So here one hydrogen. So removed as HBr. Then it forms CH double bond CH Br. So again, if you add NaNH2 sodomide, it is also dehydrohalogenating agent. It is a strong dehydrohalogenating agent, sodomide or sodium liquid ammonia. So here Br minus and here hydrogen HBr, removal of minus HBr. Here one mole of HBr, here another mole of HBr. So then it forms C triple bond CH. Red hot iron tube. On heating red hot iron tube at 873 Kelvin's temperature, if only, already I explained, if acetylene is present, benzene is formed. If benzene contains C triple bond CH, that means it is the substituent pH. Benzene ring can be written as pH single bond C triple bond CH. This ring is represented as pH, that means phenyl. pH C triple bond CH. 3 moles of pH C triple bond CH on polymerization then forms pH. So 1, 3, 5, 1, 3, 5 triphenyl benzene. So it is the answer. 1, 3, 5 triphenyl benzene is the answer. Okay, note this.